Welcome to the fourth and final part of Unit 2. In this unit, we're going to talk about acceleration. And to begin with, we're going to look at the definition of acceleration. Acceleration is the change in an object's velocity over a time interval. Hold on one second. Here we go. So acceleration is the change in. Remember, that's that triangle that means change in velocity over a time interval. And just like with velocity, where you might also see it written with a delta t, okay? It's a vector. Direction of acceleration matters. So let's do an example really quick where we do a sample calculation, okay? So when I wrote this slide, this was the best acceleration for a car, except ones that were specifically designed to race on the salt flats, like a real car, if you will, from rest from 295 kilometers per hour in 6.2 seconds. So first thing, keywords. From rest, that means 0. And that's the initial. This is the final. And so this is the initial velocity. This is the final velocity. And this is the time interval. So you can think about it as t or delta t, whatever makes you happy there. Okay? So the first thing we need to do is we need to establish a coordinate system. And I'm going to let to the right be positive. The initial looks like it's not moving. The final looks like it's moving at 95 kilometers per hour. And we're letting it be in the positive direction. I made that choice in my coordinate system. Maybe you set up a different coordinate system with your choice. We should still get the same answer as long as we are self-consistent and interpret in our coordinate system. Okay, the second thing I noticed is I have units here of kilometers per hour, and I have units up here of seconds. So somehow I have to match the units. It is easier to match the units prior to calculating the acceleration than it is to try to match them afterwards. So we have a choice to make. Do we want to convert everything to hours or everything to seconds? Right? It doesn't make much difference. So let's convert seconds to hours because we can. So 6.2 seconds equals 6.2 seconds. And then, as we saw before, there are 3,600 seconds in 1 hour. And if I put that into my calculator, 6.2 divided by 3,600 is 0.0017 hours. I rounded a little bit there. It'll work. Okay. Now I can calculate my acceleration. Acceleration is a change in velocity divided by a time, which is the final velocity minus the initial velocity divided by time. In my coordinate system, my final velocity is a positive 95 kilometers per hour. My initial velocity is 0 kilometers per hour. And the time I just converted is 0.0017 hours. Okay. So if I take 95 and divide by 0.0017, I get 55,882.4, and the units here are kilometers per hour squared. Okay. So 55,882.4 kilometers per hour squared. Now you may be wondering about the units. So what we really have are kilometers per hour divided by hours. So we got to get rid of the improper fraction. To do that, we multiply by top and bottom by 1 over hours. This one cancels that. And now I have kilometers per hour times 1 over hours, and you can see the units of kilometers per hour squared. In general, the units of acceleration will be meters per second squared in general. Okay. Okay. So acceleration is a vector, and direction of the acceleration matters. So what happens if we have the acceleration relative to the velocity in different directions? So in class, I do this by walking and illustrating, but here I'm going to try to do it by driving. Let's try drawing. So in question 1, we have the car moving at 55 miles per hour. And we see acceleration is to the west, and the direction of travel is also to the west. So for the sake of this example, this direction is to the west, right? The acceleration is to the west. So that means if I think about my definition of acceleration is final minus initial over time. And I forgot my little arrows, so we're going to go up and add them there. In order for this acceleration to be in the same direction as my initial velocity, then the final velocity has to be in that same direction. It has to be bigger. So in this case, it's going to speed up. That's the answer to number 1. So to reiterate, if this is 55 and this were 45, for example, then my acceleration would be negative, which means it'd be in the opposite direction of my initial velocity, meaning instead of the acceleration being to the west, the acceleration would be to the east. Therefore, when the acceleration is to the west and the velocity is to the west, the only way for that to happen is if the vehicle is speeding up. On the other hand, as I just illustrated, if my final velocity is smaller, then my acceleration will come out negative, meaning my acceleration is in the opposite direction of the initial velocity. So the answer for number 2 is going to be that it slows down. The velocity decreases in magnitude. Okay. The last one is hard to see. Okay. It's not quite as easy, and using this calculation doesn't help as much. So if the velocity, as I said before, is to the west, but the acceleration is to the north. Let's see. Never eat shredded wheat. So if the acceleration is to the north following a good coordinate system, I believe that makes it downward. If I did it wrong, I'm sorry, but for the sake of this example, north is downward. What's that going to do? Well, the velocity initially is to the west, the acceleration is to the north. That's going to cause the velocity to change direction. So in this case, for number 3, it changes direction, or in other words, it turns. So the word acceleration in this case means that you could increase your velocity, you could decrease your velocity, or you could change direction. Okay. And from that standpoint, there is a word that I won't use when lecturing, but you will see this word in labs. You may see it in your textbook. You may see it other way around. And that word is decelerate. Okay? There are words in physics that don't mean the same as words in everyday language. And accelerate is one of them. In everyday language, decelerate specifically means that you are losing velocity. You are slowing. Okay? But remember, as we just saw on the last slide, accelerate in physics means speeding up, slowing, or turning. We have one word that means everything. So why would I bring in another word? I don't need to. So you will not, or at least to the best of my ability, I'm going to try not to use the word decelerate because I have another word that does the same thing. Okay. So we have 4 scenarios here. Okay. Determine the sign of the ball's velocity and acceleration while or given the situation that is happening. So in situation number 1, you're told up is positive, right? So that defines the coordinate system, and we have a ball that is thrown straight up. So the velocity is upward. So immediately we can say for this one that v is going to be, determine the sign. So v is going to be positive. As a ball moves upward through the air, it slows down. And we just saw 2 slides ago that when velocity and acceleration are opposite each other, that will cause you to lose velocity. So acceleration must be downward. Therefore, acceleration is negative. It is not in the positive direction. It is in the negative direction. Okay. Number 2, up is again positive. But here we're told the ball is dropping downward. So the velocity is now downward. Well, if up is positive and the velocity is downward, that means the velocity has to be negative. But as it falls, it's going to increase in velocity. That means the acceleration has to be in the same direction as the velocity to cause it to increase. Therefore, the acceleration is also negative. Number 3 is very similar to number 1, but instead of being up positive, we now have down positive. Ball is thrown upward, so that means velocity has to be upward. So immediately, since down is positive and velocity is upward, velocity must be negative. And as it goes upward, it's going to lose velocity, so acceleration still has to be downward, so acceleration is now positive. And the last scenario, let's see, I think I have room over here. We have down positive, we have velocity downward, and we have acceleration downward. Because both of those are downward and down is positive, both velocity and the acceleration are positive. And what we see is no matter what direction we defined as positive, when it was slowing, they had opposite signs. And when it was increasing in speed, they had the same sign. If we go back a couple of slides really quick to our example here, we defined our velocity at 95 kilometers per hour in the positive direction. And notice our acceleration that we calculated was positive, indicating that the car sped up from 0 to 95 kilometers per hour. Velocity and acceleration were in the same direction. Okay. Can an object have 0 velocity? And when you see things written like this, what it's really asking is 0 instantaneous velocity. Instantaneous. Remember, the size of the instantaneous velocity is the speed, which is why the title of the slide can refer to speed and be kosher, if you will. So can an object have 0 instantaneous velocity and a non-zero acceleration? Yes. Okay. For that to happen, what I need is for it, here, let's see, if I'm going to go all the way down here. So an example is it's not moving now. So it's not moving this instant. That gives me my v equals 0 criteria. But it is moving the next instant. So here we see that it wasn't moving, now it is moving, therefore the velocity had to change, and therefore the acceleration is non-zero. Okay, option 2, or question 2 here. Can an object have 0 acceleration and a non-zero velocity? This answer is also yes. Okay, so remember the definition. Acceleration is a change in velocity divided by a time. For an object to have 0 acceleration, that means the change in velocity for a to equal 0, that implies that the change in velocity has to equal 0. Well, change in velocity equaling 0 does not mean velocity is 0. It just means that means that the velocity is constant. Could be 0. Could be 1,000,000 miles per hour. We don't know. All we know is it is constant over whatever the observation time interval is. that brings us to the end of the fourth part of Unit 2, which also brings us to the end of Unit 2. In Unit 3, we are going to take the ideas of position, velocity, and acceleration and apply them to projectile motion.